Elon Musk has launched rockets into orbit, landed them safely back on Earth, and even created cars that can drive on their own. Now picture what might happen if that same inventive mind focused fully on the skies above. In the year 2026, discussions are growing louder about a futuristic electric airplane that could mix the speed and style of a private jet with the precision agility of vertical takeoff. The vision is bold and thrilling. Imagine lifting off directly from a rooftop, gliding quietly across hundreds of miles, and landing smoothly without ever needing a single drop of fuel. This kind of idea could push the aviation world into a new era and force it to catch up with a pace set by Tesla. Welcome to Amp Drive. If you love future technology and the world of Tesla, you are in the right place. Make sure to subscribe to Amp Drive because today we are going to explore something so extraordinary that it might redefine travel forever. Stay tuned, because this journey is going to amaze you. How could Tesla design electric airplanes that combine the comfort of a private jet with the efficiency needed for everyday travel? The foundation of the concept begins with a slim, aerodynamically shaped fuselage made from carbon fiber reinforced polymer laminates. This construction reduces structural mass by around 22 to 27% compared with aluminum alloy 2024 T3, which is one of the common aerospace-grade aluminum materials in use today. By lowering mass, the design creates more room in the weight budget to allow larger battery systems. The structure uses unidirectional plies carefully placed in zones where stress is highest and woven fabric in more complex curves. These curves can achieve tensile strengths greater than 800 megapascals and stiffness levels ranging between 70 and 120 gigapascals. With a surface finish smoother than 50 microns and well-shaped wing-to-body joints, the drag coefficient can be reduced to about 0.018, which is significantly lower than the 0.025 to 0.03 common in today's single-engine general aviation aircraft. This reduction in drag could improve cruising efficiency by around 8 to 15% when flying at a speed of 300 km per hour. The wings are designed with blended roots to cut interference drag and are given aspect ratios between 9.5 and 10.5, while winglets are shaped to preserve laminar flow across more than 45% of the chord length. This layout can achieve lift-to-drag ratios of 17 to 18 compared to the 14 to 15 commonly seen today, allowing greater range without needing heavier battery packs. Vertical takeoff and landing capability is made possible by 6 to 8 vectored electric duct fans, each able to deliver between 80 and 120 kilowatts of power. For an aircraft with a maximum takeoff weight of 1,800 kilograms, a thrust-to-weight ratio of 1.5 would require a total thrust of about 26.5 kilonewtons, or roughly 3.3 kilonewtons per fan when using 8 fans. This can be achieved by duct fans with a diameter of around 0.85 meters, rotating at a tip speed of 250 meters per second. Such performance offers enough margin to hover even when air density is 10 to 20% lower, which is often the case at high altitudes or in hot weather conditions. Noise reduction is also a critical goal. Sound levels could remain below 65 decibels on the A-weighted scale at a distance of 100 meters, which is around 25 decibels quieter than the noise produced by a normal helicopter. This is possible by enclosing the duct fans, tuning the stator and rotor acoustics, and applying variable pitch blades. The motors used are permanent magnet synchronous motors with peak efficiency levels above 94%. They rely on neodymium iron boron magnets that can remain stable at temperatures as high as 180 degrees Celsius. To manage heat, a liquid cooling system using micro-channel cold plates keeps the temperature rise under 10 degrees Celsius during vertical lift periods lasting 30 to 90 seconds. The nacelles, which are built from carbon fiber reinforced polymer combined with Nomex honeycomb cores, act both as aerodynamic covers and as structural mounts. This dual role improves static thrust by as much as 12% while also providing safety protection from open rotor hazards. A redundant central flight control computer running feedback loops at 200 to 500 Hz controls thrust vectoring with a response time as quick as 0.05 seconds. The battery system is designed to handle discharge rates of 6 to 8 times its nominal capacity, which is known as the C rate. This means it can deliver the high power bursts needed for vertical takeoff and landing without losing torque. Just think about this for a second, skipping long airport lines and flying directly from your own driveway to your destination. If you can picture that, type Tesla wins in the comments because that is the future we all want to see. But comfort matters as much as technology. How could an electric plane truly deliver Tesla-level comfort while staying within aviation limits? The cabin shape and interior volume are engineered to maximize usable passenger space while also maintaining a safe center of gravity. A practical layout for a 4-seat electric airplane would measure about 1.4 meters wide, 1.22 meters tall, and 2.8 meters long, giving a gross internal cabin volume of about 4.7 cubic meters. Structural battery packs installed under the floor occupy the central keel area. This clever placement lowers the aircraft's center of gravity by an estimated 0.08 to 0.15 meters compared with a traditional light aircraft. A lower center of gravity improves stability in roll maneuvers and reduces passenger seat belt strain when turbulence is encountered. After taking into account space for structural fairings and essential systems, the usable passenger volume comes out to around 3.4 to 3.8 cubic meters, which means about 0.85 to 0.95 cubic meters of space per passenger. The seating arrangement and comfort follow automotive-style ergonomics adapted for flight. Each seat offers a width between 480 and 520 mm, with space between seat rows ranging from 900 mm up to 1,500 mm depending on layout, striking a balance between passenger comfort and available cabin room. Cushions about 60 to 80 mm thick, built from foam with a density of 50 to 70 kg per cubic meter, provide good comfort for long trips while keeping each seat's weight between 12 and 18 kg. Seats can recline up to 150 degrees for greater comfort, though this requires stronger seat frames and more track space, adding 2 to 4 kilograms of weight per seat. The aircraft's control system and cabin interface are merged into a single aviation-grade touchscreen with backup manual controls. A practical setup might use an 18-inch laminated display with a resolution of 1920 by 1200 pixels, supporting multi-touch and updating in less than 15 milliseconds for smooth performance. This display could manage navigation, systems monitoring, climate settings, and entertainment functions. Essential flight functions would still have dedicated backup physical controls so the pilot can safely fly if the screen fails. Cargo capacity is also carefully balanced. 2 compartments, one in the nose and one in the rear, each about 1.05 cubic meters, combine to provide around 2.1 cubic meters of total cargo space. This is enough for 4 large 75-liter suitcases along with extras like golf clubs or skis. The cargo floors and walls are built strong enough to carry at least 200 kilograms in each section with additional safety margins matching light aircraft standards. The loading height is kept below 0.55 meters for easy handling on rooftops or ground paths. Clear cargo loading charts are always provided to ensure the aircraft's center of gravity stays within safe limits, never shifting more than 50 millimeters away from balance. Cabin environment quality is crucial in an electric airplane. Because propulsion systems make less vibration and noise than combustion engines, designers can focus on enhancing passenger experience. Enclosed duct fans, active vibration dampers, and multiple layers of insulation could lower cabin sound to below 55 decibels during cruise flight. Exterior noise at 100 meters would also remain under 65 decibels, making the plane acceptable for city operations. Heating, ventilation, and air conditioning needs are managed efficiently, typically using between 1.5 and 3.5 kilowatts during cruise, with short peaks of 4 to 6 kilowatts during ground preconditioning. If the airplane is kept below 12,000 feet and unpressurized, these systems remain lightweight. If higher pressurized flight is required, stronger fuselage structures and more powerful climate systems add about 50 to 120 kilograms to the aircraft. Managing the balance between energy use and weight remains one of the greatest challenges for a vertical takeoff-capable electric aircraft. Consider this calculation: cruising at 300 km per hour while needing 120 kilowatts of power, a 150-mile flight would take about 0.8 hours and consume nearly 96.66 kilowatt-hours of energy. Adding a safety margin of 30% for reserves and vertical lift brings the total to about 125.5 kilowatt-hours. With batteries that store 260 watt-hours per kilogram, this means the pack would weigh close to 483 kilograms. Extending range to 300 miles would roughly double the requirement to 966 kilograms of battery mass. This demonstrates the trade-off designers face. Achieving longer range requires better batteries with higher energy density, lighter aerodynamic design, or heavier packs that push up takeoff weight. Safety and durability are top priorities. Passenger seats are mounted on energy-absorbing tracks able to withstand forces up to 16 times gravity in frontal impacts. Each seat has a 4-point harness with quick release for both safety and comfort. Batteries are housed in reinforced compartments equipped with fire detection sensors and automatic extinguishing or venting systems, keeping risks contained away from the cabin. The electrical system is divided into separate circuits, each with protection against excess current and overheating. The battery management unit monitors every single cell, balances charge, and tracks energy levels with accuracy of plus or minus 2%. All flight systems are designed to meet strict aviation certifications such as DO 178C for flight software and DO 254 for safety hardware. Environmental testing follows DO 160 guidelines to confirm reliability in real-world conditions. Electric propulsion means much simpler maintenance. With far fewer moving parts than piston or turbine engines, these motors can fly more than 10,000 hours without major repairs. Bearings and power electronics are placed behind panels with quick-release fittings so technicians can perform servicing in hours rather than days. Battery systems are built in modular blocks, allowing damaged sections to be swapped instead of replacing the full pack. Depending on chemistry, battery cycles, and thermal control, packs are expected to last 1,000 to 3,000 cycles before losing noticeable capacity. Have you ever dreamed of a weekend getaway without spending any money on fuel? If so, type Tesla plane in the comments because that day is coming closer. Now the question is, how can a Tesla airplane be strong, lightweight, and durable all at once? The answer lies in the materials used. Instead of relying on standard aerospace aluminum, which has tensile strength around 470 megapascals with a density of 2.78 grams per cubic centimeter, this design uses a proprietary alloy based on advanced stainless steel compositions. Built on a chromium, nickel, and manganese foundation with precise heat treatment, this alloy can reach tensile strengths greater than 1000 megapascals while keeping density nearly the same at around 2.7 to 2.8 grams per cubic centimeter. This provides more than double the strength of aluminum while maintaining lightness. The result is an aircraft that can endure minor bumps, ground handling contact, or even small airborne debris without denting or losing strength over its service life. The outer surface adds resilience with a special polymer coating that contains tiny capsules releasing a repair liquid when scratched. Exposed to air and sunlight, the liquid hardens and restores smoothness, often up to 80% within a day. This prevents drag from small scratches, cutting repainting needs and keeping the aircraft efficient. The propulsion system uses permanent magnet synchronous motors with heat-conducting epoxy for cooling. With no pistons or oil needs, they avoid typical engine wear and can run more than 10,000 flight hours without major service. Liquid cooling keeps them below 80 degrees Celsius even on long climbs, and with over 94% efficiency, energy loss is minimal. For operators, this means fewer repairs, no oil or spark plug changes, and stable costs with more flying hours. A tough alloy structure, self-healing surfaces, and long-lasting motors give the plane strength, safety, and efficiency, lowering maintenance and extending life. The race to build electric airplanes is more than engineering, it is about proving strength, safety, and efficiency can work together. If Tesla can achieve that balance, the future of aviation will be cleaner, smarter, and built to last. Amp Drive believes in that future, so make sure to subscribe and join us as we follow it unfold.